here as a uh, invitee for special talk to all masters and PhD scholars here. And still I'm remembering my days almost in 2006, it's almost 18 years when I first entered this department as a master student. I was being late admitted student, so I didn't have that opportunity to listen as a first day listener. But still, I remember many excellent talks during my masters. Then I moved for PhD to another university. But till 2014, I was being associated with many scholars here, and then I moved to international universities as a postdoctoral, and then now being as a faculty there. So I will be today going to talk with about some multidisciplinary research career, especially because from last almost 14 years I'm in research, and as a student of physics, I really proud that physics helped me in many times in my career and even the journey that I'm here. So as a physicist, we always have the dilemma, the frustration especially, that what should be our future, and except the teaching or research, what is there? Especially teaching is well-established field for junior, senior, or university level, and we know what is the situation right now. So I can see the frustration from many physics students across the globe, not just in the Shivaji University or in part of the Maharashtra, India. It's the real world scenario across the globe, and students, those are taking physics as a major subject. Last year, according to IOP, it is declined by 40% across the globe. And this is because that we are more inertiatic, like we know the inertia as a physical concept. And we are, as a faculty and as student, and being researcher also, we are more inertia to change the field, to go in another direction. And we stick always with the core fundamental physics, that's what we need for the society, but impactful research, impactful technology also we need. So I had PhD until physics, and then I suddenly moved to the medicine field. From last 12 years, it is a journey. I will elaborate that journey, but before that I'll go for some introduction about me. So I am associated with 3 institutions right now. The University of Limerick, which is in Ireland, from 2023. Before that I was there from 15 to 18. Then I moved to the Oxford in between 18 to 23, Poland around that. And still I am associated as an adjunct faculty for medical science division there in Oxford. So I will elaborate about Oxford and my current university. So you know, the Oxford is a small town around London, and the university is there. Oxford, London, and Cambridge is a triangle, and its triangle is around 100 kilometers from London. So this is Oxford University area view. This is like a university within the city. This is city as well, and then city within the university. So these are all colleges. They have around 37 colleges, department, divisions, and research centers. Many things are there. But you will find shopping malls around there, people living around somewhere, and other some city vibes there. It's very beautiful, very intellectual city, I would say, in the world. Like you will see the people around there are very, very intellectual, very supportive, and still I love that vibes. So you know, Oxford is being always called as a premier institute in the world because of their investment in the research and innovation. So around 30,000 students, 12,000 staff. Where I am in medical science division, we have around 4,000 faculties. And it's not just Nobel laureates, but they are making the future leaders as well. So this is a complete university pack where they teach leadership qualities as well. So 40 countries, prime ministers are expert and alumni, including the Manmohan Singh, Indira Gandhi, and even Bill Gates, he's from Oxford. 28 UK's Prime Minister, they are from Oxford actually. Until Rishi Sunak, he was Oxford alumni. I don't know the new one, but definitely he might have some links there, because whenever there is a first day induction in the Oxford, they always announce someone, a future Prime Minister sitting here. It may be UK's or it may be somewhere in the world, or businessman or the entrepreneur. So it's because of their cultural, and that comes through the intellectuality. Intellectuality, the first is that the library. So they have around 1 crore 20 lakh books in their library. It's a huge, world's top library. You may see many Harry Potter movies scenarios, they are from actually Oxford. So they own all, whatever the old buildings, they are from Oxford. Their investment for research is huge. So Oxford, Cambridge, Imperial, and then US universities like Harvard, MIT, Stanford, or Caltech, they have huge investment in research. So that's why they are some top inventor, Nobel laureates, all these. But they have a history of around 1,000 years. Another institutions, this is my primary institution right now, and I'm being associated with this institution almost for 5 years. It's small university. Small means it is around 20,000 students, but it's very new, like just 40 years ago they established this university. But the impact of just 40 years is that they are top 500 US ranking, Times Higher ranking. They are one of the top for greenery campus in the world, one of the most beautiful campus I ever see. So even river flowing through the campus, and they are around 1,000 and 200 acre campus. The vibes of this university is that the freedom that we get. You will be surprised to know that we have around 20,000 international students. 2,000 international students, 3,000 international students, but around 1,700 staff, and around 400 are the faculties, and they are from international background. Even in my physics department, we have faculty from India, Bangladesh, even Pakistan. We have faculty from France, Germany, Poland, Belgium. Even I am associated with 2 research institutes here, and even our director is non-Irish. We have 3 Marathi faculties there in chemical engineering, physics, and medicine. So it's very vibrant, very impactful, and I am actually chairing the India committee for this university from 2023, and being as a chair. So before that we are offering around 200 admissions from the India side, but right now we reach around 400. So, and next year will be around 500. That is our cap for India, and we are receiving around 5,000 to 6,000 applications every year for many courses. We are getting physics students as well for master and bachelor, because of we have full-time employment for physicists as well. So our employment rate is around 97% for all departments. For social sciences, laws, or engineering, medicine, or any other languages as well. It's because we run the COOP program. The program is a 4-year bachelor course. In 3 years, you can go to industry and work there as a 9-month as an internship. Any industry, for physicists, we prefer the analog devices, which is the semiconductor chip developer. We post on scientific or other awards, that is the medical device industries, or many times they go in the automobile sector as well, other electronics industries. Engineering, medicine people, they go. Law, they go into the court and others. Languages, they go somewhere in the media and all this. And then 4th year, they come back again and they do the 9-month research project. So they have experience for industry and research. And then they choose usually where they want to go. So most of these, their 9 months stay in the university, in the industry. They get offer from the industry that just finish your degree and come back as an employee. And that's why we have huge response from the international students, especially for master courses. We don't run that program, but for masters, it's a 1-year master, and our country gives them 2-year work visa to all students, so they easily get absorbed by the industry without any hassle for visa and all this. That is the problem with the US universities or other institutions. So now I will come to today's talk. I will start with what kind of research we do, and then I'll go with my own journey, how I transferred from physics to medicine, and what in the future I'm going to do, and how it is impactful for any kind of researcher. It's not just for PhD or others, but those who are masters or just entering in their master's course, they may get influenced by this kind of journey, like we can have some different courses or different career stage, not as a physicist, maybe just a semiconductor or solar cell or any other devices, but we have something different future in the different field as well. So my prime area of research is cancer. I do most of the studies or research, especially cancer lab. I have 4 PhD students, around 2 are new joining in September, and 2 postdocs. And they all from different background. I'm a chemical engineer, I have a statistician who is doing machine learning, I have medical physicist, physics, then 2 are from physics, a biochemist are there. So even now I'm recruiting a 1 veterinary doctor as well. And many doctors, they come in my lab for intern, like MD doctors, MBBS doctors, as a research interns. So let's start with the concept, why somebody get the cancer. And you are hearing that word every time around. Every day somewhere your relative, somewhere from your family or somewhere from around you is getting cancer. Yeah? And it has around 1,000-year history, that disease that we know. And why it is dominant? We have cure for COVID within a year, but why not for cancer? It's because of the problem. Like we always follow these kind of traffic signals, and that have the meaning all over the world is same. Yeah? Wherever you go, you will find the same signals in UK, in India, in Europe, or in USA, or in African countries. Most of the European, American, Japanese, Korean, Australian traffic flow is controlled through these kind of signals. So they are very well mannered drivers, and that's why usually flow is very, very clear. While when we compare our Asian countries, we can see this kind of flow. Yeah? And this is like in physics, we have 2 states or 2 states of the matter. We call the I forget most of the physics, but it is most organized and unorganized things. Yeah, like in chemistry, we know the reversible, irreversible. Similarly, in the physics, we have ordered state and disordered state. So even ordered or disordered, even disordered following the rules, at least there is no harm. But even in ordered states, there is a problem. Yeah, in the solid state, we know the defects. The crystals have the defects, and it's similarly, even there is a bad driver in ordered state, and he can make the problem to all of them, to all of ordered state. And this is what happens in our body actually. So our body is actually composed with the trillions of cells, the organized structure, coordination between each organ, and all these mechanisms. So can we compare our body with at least one Airbus, which has at least 500,000 parts, 5 lakh? What do you think? Is it feasible? Like our body and the one aeroplane is the same, because aeroplane is big, and when you sit there, you can see many components there. But we can't. Actually, aeroplane can be compared with our single cell, yeah? Not even body. So you can imagine how complex the body physiology. And what happens with the cells? They have cell cycle. That is not the fundamental unit for our living systems. And they reproduce. It's not just copy paste like viruses. They reproduce. Means new cell comes with the proper nature selection rule. And that's why a new cell coming means they are actually assembling their own 500,000 parts again without any defect. So you can see the margin of error. There might be an error. And from where actually it comes? It comes through the DNA. So 1,000 trillions of cells every day, they die and grow. And even when you are listening my talk, maybe some of billions of cells, your own cells are died and new hairs already in your body. And this uncontrolled manner, a bad driver in organized state, can create the problem. That problem is a cancer. So usually happens through the DNA. DNA is a fundamental for all living systems. And if there is something problem, that problem dominates the system, that mechanism is called the mutations, especially in biology. And that mutation causes the defects in organs, and at the stage they grow very fast, uncontrolled way, and that is what the cancer. So it's not just one generation where one cell is mutated and the next cell is cancerous. No, they have actually 1,000 million generation as well. But every day trillions of cells dies and they grow new. So the mutation rate is again very high. But our body has the system, our immunity and other physiological systems. They always check this. Is there any defect in normal cells, and they kill that. But at some stage, they hinder, they go out, they don't send signal, and we get the cancer. Similarly, if someone has a cancer or body has something defectful, we have our natural mechanism. So usually in autumn, we know the leaves, every 3 leaves that. It's because it is a natural selection process. Similarly, our body follows, our cells follow, single cell follows, and they die by themselves. This is called the apoptosis mechanism, that is the cell death. But usually in cancer cells, what happens? They get some more protein protection, like in coronavirus. Why did we call corona? It's because they have protein layer on the surface, and inside that surface they have just RNAs. So that is called the corona. So similarly, these cells, that defective cells, they have new proteins, and that proteins don't allow them to die naturally. And that's why they grow, and they get more energy, and they dominate. So once they are dominant, something happens in that organ, that is the tumor. You know, this movie is it's Oscar winner movie from Korea, Parasite. Yeah, and they showed how a poor guy can dominate the rich guy. Yeah? This is what the psychological mentality of everyone. If someone gets space just for job, they try to accommodate their family members, they want to their own home and all these. Similarly in our body as well, when these cells, actually tumor is not from outside, it is our own cells, but they dominate and they follow this parasite mechanism. So the growing tumor is like parasite, and sometimes they need more nutrition and oxygen, and that's why they need the blood supply. So initially these cells grow, but they don't have blood supply, but at some stage they get their own blood supply. That process is called angiogenesis, and once they get the blood supply, they are again dominant because they get the nutrition. Some of these cancerous cells go into the blood and they invade other organs. That is called the stage 3 around metastasis or stage 4 in cancer, which is incurable right now. And they go everywhere, kidney, brain, somewhere. So now, what solutions we have? We have already well-established solutions from late 90th centuries, like chemotherapy, where we use the drugs, especially chemicals, but they comes with the side effect because drugs go everywhere, like our paracetamol or Indopor, that is we get for the pain relief. Even you have headache pain and the pain in the knee, and you take the painkillers, both headaches and the others. Means all pain goes for short while. It's because it's not a systemic, it go everywhere. The same happens with the cancer drugs, and they comes with the side effects like hair loss, anemia, low glucose level. Radiotherapy is well established right now. It is a physics actually. We are using the high energetic waves, maybe gamma rays or X-rays, to kill the cancer cells, but we cannot use it again and again. And it sometimes damage the organs, and sometimes due to the radiotherapy, some people get the cancer. Surgery is the best example, tumor we can say, but not all, like pancreatic, liver, other tumors are very difficult. The breast one, the oral one, or maybe a prostate one, uterus or cervical, they are easy to remove, but they come back, and brain tumor as well. Immunotherapy is what, and here we are working right now, which is like our body has natural power to kill cancer cells, but cancer hides from that. So we have to activate our natural power again and find out the cancer tumor, and or even in metastate where cancer is everywhere, find it and kill it by our own immune cells. So we have 6 types of immune cells Um, in cancer research, in every kind of research, there is a basic era. So like we are in the around AI era. Yeah, the last 2 decades are nano. You know, from 2000, especially everything was nano. People were thinking about nano. Now they are thinking about AI and machine learning. Similarly, in cancer, there was biochemistry era. They were thinking it is biochemical mismanagement in the body, and that's why somebody gets cancer. Then they realized that there is genomic factor as well. So it's DNA mutations, and they cause it. But now they understand that along with the biochemical mismanagement and genomics, there is another is the metabolomics, like our diet or the food is another factor, or the energy especially, the cell energy. And we are now doing our research on the metabolic activity of the cancer using the physics. So when we go into numbers, this is very interesting. How many drugs we have right now? We have around 900 drugs in the market. And they are dominant. We don't need new drug actually for the cancer. They are already there. But the problem is they are not very specific. Yeah? So chemicals, they don't know where to go. Yeah? They don't have that ability. We have to make this ability. And here nano medicine comes in the role that we can package them. Like you know the AM and FM radios. So what's the difference there? Like AM is an amplitude modulation and frequency modulation. In the AM and FM, we use the carrier, especially in the AM. So like we have to go Mumbai. So what are the ways we have? So we have train, we have bus, flight, our own car. But there is another way as well. We can walk. Yeah? It takes a long time, but we can reach. We see in the COVID people walk 600, 700 kilometers. But that means you need more energy and many other factors. That's why we modulate them. We use the carrier waves to modulate them, and then coding and decoding happens. Similarly, in a drug delivery treatment right now for many diseases, we can modulate them using some package, and then we can release that package and drug. So this is now market coming for especially for the cancer research. Now what is the problem? Problem is the targeting, not a new drug. Nobody is right now working on the new molecules or new drugs for cancer. They all more working on the targeting the cancer. Might be antibody based, it's like proteins, or maybe DNA based, that what we are working on the aptamer side. We are now shifting to the peptide one as well, a short part of the protein. And then we are shifting towards the very targeted aim. Now, why we have to think interdisciplinary way? And this is one example. Is that who got the Nobel Prize in the medicine? Give one example. I was reading this story in 2020 around when I was in Oxford, and then I developed a project. We got the 1 million funding from Science Foundation Ireland. And how one news can influence your mind and how you can think it differently. This is one example. This is the guy who is the anthropologist. Do you know about anthropology? Anthropology, have you heard this word? So what it deals? What is that science? It's a science where they study ancient people, their behavior all like Neanderthal, then sapiens, now we are Homo sapiens. Yeah? So he was the guy who is studying these Neanderthals, like mummies. Yeah? They are in that era. So he went to the Egypt to study that mummies, and he tried that all their preservative and all. And then he realized that I can understand this, but I can't do the research here. So then I need another knowledge. Maybe I'm lacking something, and then he went back to Sweden and he did MD in medicine and then PhD. So from anthropology PhD, then he went again for next journey into the medicine, and then he became a medical doctor. He went back again Egypt after 10 years, and then he did the lobbying with Egypt government, many international agencies, that he want to develop. He just wants the DNA from that mummy. It's not easy to get that. So then at a certain stage, he proved that I can make something different. He has a lab in Germany then. And then he got all permissions to carry out the research. And what he did, he actually made a mini brain using the Neanderthal DNA in the lab. So another guy from Canada is now in USA. they both developed this brain model for Neanderthals. And what they modeled there, like why disease follow different pattern. Yeah? Simple, like in COVID, you see, like your family members, suppose there are 4 family members, one got the COVID, 3 didn't. Maybe 2 got, the 2 not. Maybe 3 got but 1 not. Husband got but wife not. Yeah? Father got but not mother. Especially babies, they don't have, even young generation until 14, 16, they don't have COVID. And why it is? He studied with using this model and he established that hypothesis, or he proven that such kind of diseases follows, it comes through their own DNA. So our own DNAs are impactful, like someone get the COVID, someone is more resistant to the viruses, someone are not, means their immunity. So how immunity is evolving from Neanderthal to sapiens and Homo sapiens. And that was a COVID era and he got the Nobel Prize. But what's surprising for me is like he made a brain from DNA, and then I thought, can we model the tumor in the lab? Because the problem right now in the cancer research that we do the lab studies and then we go for the animal studies and then humans. What is the success rate from lab to animals? It is just 1% around. Like all lab experiments we get very fancy results, publishable and something that we can make the noise. But in the animals it's difficult then. Then after animals, even now we get good results, we publish and all these. But what about humans? The success rate is again 0.5%. So most of the journey is around 15 years from lab to human trials. And then people thinking is that bypass these hurdles, barriers from lab to direct market. Even we can bypass the animal trials and human trials, clinical trials. And then we started our journey to understanding the gaps. What is the problem with cancer diagnosis? What are unsolved questions? And being physicists, we are always curious about the universe. Yeah? I just have one question. Which science or which fundamental is the first in the universe? Who is the first? Is it biology? Is it chemistry? Or is it physics? What do you think? Have you thought about that? Who is the first? Is physics, chemistry, or biology? Or all together they are? What do you think? What is the base? What is the fundamental of physics? Even classical physics and quantum physics. What we deal with the energy. Yeah? Then this energy makes the matter. Matter is because of energy. It's bonding. Then matter is mostly part of the chemistry. And then the real bonding, the living organisms comes later because of the bonding. What is the DNA? DNA is a carbon, nitrogen, hydrogen, oxygen bonding, nothing more than that. Yeah? Our lipids, our proteins in the body, even our blood, hairs, they all are bonds actually. So to strengthen the bonds or keep them in that state, we need the energy always. It may be sometimes transfer energy, we take the energy. And that's why physics is the first fundamental in the universe. And there was a theory by Socrates who first proposed, who first given the philosophical thoughts that we can cure something with the energy, some diseases and many things. And the fundamental energy in the universe is again the light. Yeah? We are alive here or we are here because of the light. What is the reactions? So in the universe, especially on the Earth, what is the difference than the other planets? Just we get the good sunlight and we have the water. Soil is everywhere. Even water is there but in different states. In some planets it is on the condensed state, some have the solid state water as well. But the Earth has the 3 states. And there was an interaction between light, water and matter. Especially water comes into the matter as well. But light and matter interaction is what we have. Even in photosynthesis reaction, those are vegetarian people. What they eat the light actually. They absorb the light as a catalyst and then reaction happens. What happens there? Glucose is converted into the ATP. The same happens in our cells, but we don't use the catalyst there. So similarly, physicists can come to even 6 physicists, as I know, they got the Nobel Prize in medicine. Yeah? Even those who solved the DNA structure, here they are physicists. MRI, the medicine discovery, that is physicist. Even 2-3 years ago, one guy got the Nobel Prize for medical discoveries, especially laser based. So we can think for unsolved question. As a being trained as a physicist, we are critical thinker. We can think that there is an electron who has uncertainty, who has a dual behavior, but proteins don't have. That biologist has the barrier. Chemist always thinks about the bonding. So they always model things. But physicists can imagine. And then we started with unsolved questions. Why cancer goes somewhere? Like someone has a liver problem. Can liver go to the kidney and ask the help? That I need help, and just liver itself is a regenerative organ. But suppose kidney has a problem. Kidney cells never go. But cancer cells go. And they go into somewhere and they ask the help. And that organ helps them, especially in the breast cancer. Their breast cells goes to the brain, and then brain cells help them to develop there or stay there. So why this happens? What is the mechanism there? And that is the thermodynamics. So then we were thinking about, can we model this tumor in the lab? And yes, we can model, we can do it, but how we can target? And then again, my own expertise comes, like the nanomedicine. We can use some kind of organic structures. There are being now polymers and liposomes. These are already in the medicine. Inorganic still facing the much problem, like magnetic. This is my core. We are working on gold, silver, carbon as well. Organic, inorganic hybrids, we are working on there. But these two streams have real problems because they have high toxicity, many other problems than the polymeric materials or the organic materials. Now what we add again, that as I mentioned, the fundamental of the universe is the light. So we use the light activated therapies, that is the in region of UV or UVs we are feasible for any medical application, but visible region or infrared region, which is of more interest. So we use the light, magnetic field as well, ultrasound, radio frequency, we have some mechanical forces, X-rays, temperature gradient. So using magnetic field we do the temperature gradient. Using light as well we do the temperature gradient. So one form of energy we use to activate another form of energy. And currently our research is more on the therapy and diagnosis, that is called the theranostics. What knowledge gaps with the nanoparticles as well. So human translation is very difficult because we are stuck with animal models and lab models. Diagnosis, we don't have proper diagnosis until and unless we don't find the symptom. Nobody goes to the doctors. Yeah? And then, especially in cancer, it is also late stage diagnosis. Therapeutic cargo, that is what the problem. Every pharmacist, chemist, they are targeting here. Physicists coming here as well. Now, what we are developing? We are developing a very multifunctional gold magnetic materials. This is one, but right now we are shifting from magnetic gold to the gold polymeric or gold liposome nanoparticles. But this is my true area from last almost 14 years, and I love magnetic materials a lot. They are very fancy. So what we are developing, very simple iron gold core cell. For physicist, chemist, or material scientist, it looks very easy, but it's not that. We need to make the two cores from metal surfaces. And as a classical or quantum theory, it is impossible. The two metals comes together without any bonding. We are trying to do it. And how many years we are struggling? Almost 10 years. We are struggling to get the iron oxide as a core and gold as a layer. But somehow we succeed during my Oxford stay, and we are now going on the next stage for getting the very sharp, clear core cell structures. Using the simple, then we developed this simple. Right now it is simple, but it took around 3-4 years to establish these reactions and processes. But we got at least very good small size gold and magnetic nanocores. Especially we want them for CT and MRI application. In one for magnetic activation and light activation, because gold is gold absorb in visible region as well as somehow in the near infrared region, so we can absorb the light. And of course, magnetic materials are always excited in the magnetic field. So we do many hemolytic activity, like their interaction with the blood, because in future we think it will be injected to the body, and there is a basic camp like how they are interacting with the blood, especially it's called the hemolytic, how they are affecting our hemoglobin and how they are affecting our red blood cells, and we are almost in good results at almost less, more around 40% hemolytic activity for the time. But we need to improve it again, so we are using some polymers, then other conjugations. Then we are using the engineering as well. So we 2 years ago we designed this device, a small laser-based device, because we can activate these nanoparticles as a multimodal therapeutics, so they can absorb the laser light. And this is actually a very small device. So right now people are using big lasers and sophisticated optical labs. Here we don't need. Thanks to our collaborator from Poland, he's an electronic engineer who developed it. And then we have thermal cameras and all these. So what we do, we excite this nanomedicine under the laser light, and then we map their temperature and other activities, so we can utilize that temperature to kill the cancer cells. But why they get died with the temperature is because of their natural phenomena. Usually our body has around 37-degree temperature all the time. When we get the fever, it is around 38, not more than that. Somebody has a 39 temperature, means he or she will die within some days or maybe in hours as well. So just 2 degrees centigrade makes a huge impact on our body. But especially in cancer or in normal cells as well, they can sustain for shorter time up to 45 degrees centigrade. But cancer cells, they start to die after 40, and we can completely kill them around 45. But it's for short period, not for day or hours. So we use that therapy to kill the cancer cells. So these are the breast cancer cells, and you can see the great redness, they are died over the time within 30 minutes. But it is in the lab. So I told that we gave the very fancy results always. We know that there are the drawbacks, and then after reading that story of the anthropologist from Sweden, I started working on the modeling the cancer in the lab in a 3D environment, where actually our tumor in the body is like. But it's not that easy again. We have many, as I mentioned, it is one cell is like our Boeing or Airbus. You can imagine how tumor is complex. So we started 2D to 3D environment culturing. Now right now all pharma industries, they do the 2D kind of culture. So all their drug testing happens on the 2D, like surface growing. We grow the cells in the surface and give the drug, and it is homogeneous because it is all over distributed. While in tumor it's not. And that's why we are shifting to 3D one, using different techniques. So even that 3D modeling has many mathematical, computational ways. So I have my mathematical collaborator. I have specially one statistician who is doing the modeling for machine learning and AI things. And also we are now doing the biocomputation. Computational people now helping us to model from single cell to the millions of cells. The tumor has trillions of cells. So what will be their nature? But usually they follow the mathematical equations. We start from the 1 to the plateau there. And usually when tumor spreads, angiogenesis means they get the blood supply, they get the plateau, and they invade, means they start to go somewhere, because they are saturated there. So similarly, we observe this behavior in the lab as well. So when there is a saturation for the tumor, this is a 3D tumor cells, and they start to go. So they leave their environment and they go into somewhere, even in the petri dish. We model before doing experiments, after doing experiments, we got the same results. Now, what kind of cells we are using? So we especially working on the brain cancer side. It's very tough to diagnose and difficult to understand their mechanism and their heterogeneity. We use the glioma cells, where most of our outer brain, and then neuronal cells. Neuronal cells is everywhere in the body, our neurons, but they are more dominant in the brain. So some people get the neuroblastoma, that is the cancer for the neurons, glioblastoma, medulloblastoma, that is more on the other part of the brain. But these kind of cells, they interact each other in the brain. So we are developing the same model in the lab. Like what happens when we co-culture two cells together, and how fast they grow, or they don't grow, or they stop, or they die. And we found that when adding the co-culture, means different brain cells with neuronal cells, they grow very fast. Even we did experiment with the breast cancer cell as well. In breast cancer, with neuronal cells or glioma cells, they grow fast. And that's why women get the metastasis at a late stage from breast cancer to the brain cancer, because brain cells support them there. Then we use this nanomedicine, especially drug conjugated to deliver drug. This is a drug actually, doxorubicin, which is ideal cancer drug, and every cancer researcher uses as a model drug there, because it has natural intrinsic fluorescence, so we don't need to tag them to see under the confocal laser-based microscope. So we use different chemotherapeutic protocols. We come from different layers because it's a 3D environment, so we have to scan in the 3D way. And somehow we achieve drug delivery into the 3D ways. And here again we use the physics, like our materials are magnetic, so we use the small magnetic field there. And under the magnetic field, the drug delivery is very high. So these particles, they can be there for long, or they can go into the cell as well, and without any magnetic field. Especially here, like we use the mathematical models, how drugs go into each cell, yeah? And what happens, they die or they live. Like green region is always live region, the red one is died region with the drug. This is what we are now going to publish soon, but still our work is ongoing, different ways. Usually when patient is treated in the in hospital, they follow the chemotherapeutic protocol. So always 3 days, then 3 days off, or 1 or some month off, then they do. So ideally, usually we found that around 24 hours, 74 hour drug treatment according to the clinical protocols, and especially for brain and neuro cells, and these are for small children, like we call pediatric patients. They have different problems with brain cancer, and we are developing models for them as well. What happens with their tumors, because we cannot treat pediatric, these small children. They born with cancer actually. Even newborn babies have cancer. You don't know, but just visit cancer center anywhere in the Kolhapur or Miraz or Mumbai, Tata especially. You find many children, they are just lying on the bed or somewhere, and they have brain cancer, blood cancers. So why this is? It's because of their parents or many other environmental factors, and we cannot treat them usually for radiotherapy or chemotherapy because they affect their future life. Like radiotherapy, they makes them infertile in future. Chemotherapy is very toxic. They may die with the chemotherapy. So they usually treat with the surgery and all these. So we are now developing models. What happens when we treat them with drug? How it works on these pediatric patients, especially in cellular level. We are monitoring their activities for over the time with doses and all this. But all this is in the lab still, because this model is in lab. We are getting good results, but not the clinical relevant result. We have 30% still cells are alive there in a 3D environment, and we need 100%. Otherwise, they have more aggressive nature and they come back. Like cancer comes back again because of this. So we are now going on the next stage. In between, I will just explain about one of our different strategy that we recently patented and transferred to the company. That we developed the gold nanorods, small gold nanorods around 20 nanometers, cultivated them with the many functional molecules, anti-cancer, and bacterial molecules, or other molecules, drug as well. And we excited them under somehow visible near infrared region. And they absorb the light there, especially infrared light. And we get the heat over the time. And this we can use to kill the bacteria, especially in the hospitals. Hospital acquired infections. Some patients, when we admit them in the hospitals for especially surgeries, and after surgery they get the infection and mostly patient die. And doctor says they have sepsis or septic something. Yeah, sepsis is a disease. It is because of the drug resistance bacteria, and many of the hospitals they have acquired infections there. Their medical devices, instruments, beds, they already have infected with these bacteria, and over the years they get a resistance with the antibiotics especially, and then we need sterilization. Yeah? To sterilize them, they usually use the UV or heat. Usually earlier days we were using syringes, we are heating it. Now we are using the new one, but I still have in my childhood we are using the same syringe after heating. It is a sterilization process. We are killing bacteria at around 120 degrees centigrade. But we don't need right now that one. Even around 50 degrees centigrade, we can kill that bacteria under the laser light and nanoparticles. Not alone with the energy, but we need something catalyst there. That is what the nanomedicine. But physics and chemistry plays a crucial role in the biology. This is one example. And we got actually an award for this technology from the European Commission. What's next? So what we are now modeling, like we went from 2D layers, yeah, to 3D. Now we are going for the patient. So we are taking our patient samples, tumor sample, and we will be growing them in a lab in a 3D microenvironment, and that is what the tumor in the lab. Or we are using the microfluidic chips to gauge the real time conditions like blood flow, immunocells, and other cells. That is called the tumor on chip. One of my chemical engineering students is working on the tumor on chip project. Cancer nanovaccine, this is another fascinating area where two of new students will be joining, which is more on the activating our own immunity. It's like nature gifted us our own sort of defense mechanism, that is immunotherapy. So like our immune cells can kill cancer cells. What happens over the time, cancer cell, tumor, they hide from that immune cells, and then tumor dominant, and then immune cells forget about that they don't know that there is a tumor. Then we have to recall them. We have to go to these immune cells and have to activate them, that just go and find the tumor in your body and kill them. That is what the immunotherapy, but it's not easy. That is the fancy word right now as a cancer vaccine that is coming in the market. So we are developing peptides especially to activate these immune cells, and we are delivering this peptide using the nanomedicines, especially for breast to brain tumor metastases, and then pediatric cancers, then other cancers we are exploring that. Now, this is what about the research. Might be your physicist, you are unknown about many concepts that I was almost before 2010. But now I understand many biological concepts. At least I know protein means what, DNA means what, cells means what. Like similarly, biologists don't understand what is the cortex. Yeah? They don't know. Even physicist has that problem like me. But it's concepts, like every word in physics, chemistry, biology is a concept. So like cortex is a concept. It's not just one word. Molecules or bonding, these are the concepts. Similarly, in the biology, it is proteins, lipids, others. So to understand that, I will just go with the one example. My own story, like in secondary school, I had just the normal marks in physics. It's not a very good marks in maths, chemistry was weak, and I left chemistry from 12th. But biology was dominant. But I decided during my BSc that I will not take the biology. I will go with the traditional A group like physics, maths, stat, and electronics. And then I came for the MSc pure physics here. So I still remember professor was teaching me thermodynamics, classical physics, and then quantum physics. These are my actual lectures, and we were thinking that we will develop something quantum science, which is just imaginary. Still we have debating, is there real quantum world or not? Still we are following classical rules for almost over 99% application. But after that, during my PhD, actually my supervisor, who is our former faculty member, Professor Esishwar, he insisted me to just learn biology. Don't do the experiment, but at least understand the biology. So we were doing some biology there, not pure biology, even we are struggling with the facility infrastructure. But I was going to some of the biology centers in Pune, Bhabha Research Center, and then I got interest. But one sudden change happened after PhD, my first position in the South Korea. Actually, before writing thesis, I got this offer from Samsung Medicine to be a postdoc there. And it was a medical school. And we have doctors, clinical doctors, protein chemists, all kind of package there. Biochemist, microbiologist, and I was the only physicist there. And all they are actually more biochemist and microbiologist, clinical doctors. But I learned a lot from them. How physics experiment works, how chemistry experiment works, and how biological experiments work. And the main difference between the physics, chemistry, and biology is that experimental procedures. In biology, they are not reproducible. They struggle a lot to get the same result every day. In chemistry, the struggle is almost less. Yeah? If you set the parameters for reaction, you can get the reproducible result. Every corner of the world. Even in physics, especially in the optics, it's very difficult to get the reproducibility. But once you set the experiment and the system, you might have better chances to get the reproducible result. But in biology, it is almost every day the researchers, they have the frustration. And this is what the culture between three different sciences, how they deal with the same problems and what the difference. So there I learned to be more patientful for the biological experiments. And when you are combining nano things, especially inorganic nanomaterials with the biology, is again more challenges. Like polymers, lipids, or other biological molecules, they follow somehow some traditional procedures, but these are the new medicines, they don't follow biological rules. So we were doing cancer and bacterial infection research. Then I moved with my own fellowship in the University of Limerick. This is our now research center, our university. Then I went there in 2015. It was just inaugurated. Then I was working with the physics department there. Still I'm now faculty here, and my area for research was the same. So like doing the same thing in different environment, different perspective. So in Korea it was doctors, medicine people, biologists. Now here physicists, pharmacists, chemists, especially this department is very dominant. Now I am here supervisory board member of this department, as well as my lab and offices are here. This is gifted by the Analog Device, the chip making company, because he's our CEO, alumni. He's our alumni CEO, and he gifted 40 million to our university, and we established this department, and we have all state-of-the-art facilities here. In meantime, in 2018, I went to Germany as well, in 18 Poland, in 19 before COVID I was in Switzerland. So that was biomedical engineering department. So mostly with the biomedical engineers, it's engineering perspective with the same kind of research. Here it's different. Like in University of Zurich, I was working before COVID. It's called the Vet Zoo, that is veterinary medicine. And that was a miracle for me. It's a game changing, means my life actually changed there. I learned a lot from doctors, and they are not human doctors. They are actually veterinary, means animal doctors. And they are surgeons, they are psychologists, they are brain therapists, they have everything there. They have LINAC, the LINAC is the guest on top facility for any kind of cancer therapy. They have MRI, CT scan, everything for the animals, not for humans. So you won't imagine, I saw they were doing MRI for horse. Even they were doing MRI for the rabbits and all this. And we are working on the canine patient treatment, like dogs, they get the natural cancer. Some animals, the dog is one example, they have natural cancer. Other animals don't. So we were working with them. And then I moved to Oxford. That was still I'm associated with this department. Especially it was a women and reproductive health division. I was associated with the National Health Services UK, that is NHS, as a consultant. So we are consulting about women because that is maternity, especially reproductive health department. So we have women from pre-pregnancy, after pregnancy, all there. So I learned most of the women's psychology there, especially how their hormonal imbalance impact their life, why they are very aggressive after pregnancy, after delivery, why they are very cool during their childhood and why they are very aggressive after pregnancy and all these. Still, I learned that, and I am translating one of the book right now with one of the publisher from English to Marathi. That is the Female Body Bible, and that's what all about your all from here to your all the things. What is the hormonal imbalance and all this? And I learned actually there during my stay. So this is all about my research, then the physics things, and then my journey, and what in future we are going to do, especially for cancer vaccines. We are adding the magnetic field activated cancer vaccines and light activated cancer vaccines, and we have collaborators across the world. So not just from the island where I am right now, but around 40 collaborators I have. I am associated with many European Commission's cancer mission. Just 2 days before, Irish government nominated me for the another mission that is called the magnetic particle imaging, which is another revolutionary physics-based therapy for any kind of disease. Especially, they will replace the MRI machines with small MPI machine, magnetic particle imaging, and it is called physics, magnetic physics. So they have the 250 scientists across the globe. We have 28 education and science minister, health minister from the European countries, and we have around each country can nominate only one nominee from these 27 European countries. So I got nominated from the Irish government to be a management council member for next 5 years. So we will be making the policy for that device, especially medical device, and how it can be translated to the hospitals or the medicine. Along with, we will be doing the research as well, and then the clinical things. So we have team from the hospitals and all these. So these are our good collaborations. We have the people around, and we are always open, especially for the collaborations for any kind of scientific activity. But unfortunately, I'm very strict with the cancer and all these. And many physics department, their research is more on the other, maybe a solar cell or the supercapacitor or a battery, especially now dominating. So unfortunately, I have a big barrier to collaborating with the physicists, but chemists are some physicists also work with us, pharmacists and chemists, of course biologists, immunologists and clinical people want to work with us. So this is what we do. This is my own journey as a physics student who is listening the lectures, just sitting like you, and now to be here to influence you that take the physics. I love physics, I'm proud for the physics as well, but think differently. Physics will be not your life at all. You have to learn something, like as a physicist you have to learn machine learning languages, Python and all these. You have to learn the design, how engineers design any devices. So I teach the medical instrumentation to my physics student. I teach them designing as well. Simple transducer that we learn is just a conversion of energy using the electronic components. So that transducer, how it is designed, as a physicist, how you can think it. We teach Neuralinks as well, Neuralink device, how that works. It's again physics. They are taking the neuron signals, using the batteries, they are storing it, and again activating our other signals, like someone has paralysis, so they lose the motion, the part of the brain is inactive there, so they are using the electrical signals to activate it again, so we'll get the more coordination. So all this is physics actually. Whenever I talk with doctors, I say from stethoscope to MRI or LINAC or anything, it is physics. But the problem with this, we don't learn the design and technology. So as a fundamental science students, I must say we have to learn something differently. And this is what the future, and who taught me, who is actually my teachers, they taught me this, especially from my masters. When I came here, I saw many of my PhD seniors, they were going abroad. So then I realized I can be, if I do PhD, a quality PhD, maybe I will go abroad. So maybe I'm sure many of you will be influenced and you will be a next generation researcher who will change track, or maybe from traditional one to the different one. It's not that easy. You have to struggle every day with many other people. Like medicine people, they are very energetic, they are very toxic guys for any kind of research. They don't like research especially. They always think that, oh, X-ray machine is okay, I can diagnose something. But they want new technology as well. But they think I will not replace this X-ray machine or the MRI machine which is costing crores of rupees. But they want some more superficial technology. And this is what physicists are doing across the globe. Be a part of that, learn something new, especially from daily life. Similarly, what I read one news before going to sleep that someone is developed the brain in the lab. Why I can't develop the tumor in the lab? And we got the 1 million euro, it is almost 9 crore rupees funding from the Irish government. So this is what some game changing. Our start with the D, like research start with the discussion. So discuss. Yeah? Unfortunately, we are not discussing on that way. Actually, we are less with the time, but I have another presentation that I always ask students, faculty that use the two-way knowledge transfer mechanism, discuss, transfer knowledge, criticize each one, thinks differently, and discuss with that, and then start research. It's not a one-night miracle journey that I'm discussing something I hide and next day I'm developing some device or product. It's not. Some people have waited full of their whole life. Like in 2019, two of the professors, one from Canada and USA, they got the Nobel Prize. One was a lady, she was just 42 years old. And her one publication got her the Nobel Prize. That is the laser one that we are right now, all laser technologies using in the medicine. And another guy who was 93 years old, who was developing the laser treatment for 30, 40 years. So sometimes you can get the success for something within a night, not a night, but her journey was inspiring as well. She struggled a lot. And for some success, you have to wait a lot. So even almost for 12, 13 years, I'm this research. I'm struggling a lot. We fail many times. We don't get funding. Our papers not published. People criticize us. Sometimes our friends fail us in many ways. So be acceptable for that. And being a student, being a physicist student, be open for the knowledge. So thank you so much for your kind and patient listening. And I always believe on this somehow to a knowledge transfer. If you know some questions, if time permits, I'll be more than happy to take some of your questions. Thank you.